Now we can finally define metric on this set by using the norm. So I'm not expecting you to really know anything about norms in general. I really just want you to know about this one. I'm not expecting you to know what a norm is. But those properties that we proved just now, those three properties of this thing that we looked at, the triangle inequality, positive definiteness, and the scaling property, that's what makes it a norm. What I do want you to know about is metrics. So our goal is to make this into a metric space. And here's the metric. So define D from the space of linear maps, across the space of linear maps to non-negative real numbers, like this. And you should verify that this is a metric. It derives its metrichood from the norm properties that we just examined. So for example, positive definiteness, the fact that the distance between A and B can only be 0 when A equals B, that's going to be a consequence of the positive definiteness of the norm. The triangle inequality will be a consequence of the triangle inequality that we just established for the norm. So this is a metric. So now this is a metric space. That means we can talk about the distance between two linear maps, as long as they have the same domain and codomain. So as long as they're the same, they're linear maps with the same type signature, then you can talk about the distance between two linear maps. And that brings with it all of the metric space concepts. So you can talk about open subsets of this, you can talk about open balls in this, you can talk about closed sets, you can talk about limit points, you can talk about continuity of functions that map into this or map out of it to other metric spaces. You can talk about limits of functions. So all of the stuff that comes with metric spaces is now available. And I want to, before ending the course, I want to just show you why one might want such a thing for the purpose of working with derivatives in higher dimensions. But first, let's just look at an example. So let's just consider the distance between two linear maps. So here's an example. Let's say I and R, let's call them. I will be the identity and R will be a rotation. Those will be linear maps from R2 to R2. So that means what I'm about to define. Yeah, so define these by Ix equals X, and Rx is going to operate by a rotation matrix. So maybe 0, 1, minus 1, 0. So this will be a 90-degree rotation in the plane. These are both linear maps, the identity and the rotation. So R and I are both elements of this metric space, the space of all linear maps from R2 to R2. Okay, so this is a 4-dimensional vector space. If its dimension were lower, like 3-dimensional, 2-dimensional, then we could imagine plotting R and I as points and visualizing those points and trying to visualize how the distance between them works. But the space of linear maps from R2 to R2, that's a 4-dimensional vector space. So maybe we have to get a little creative to try to visualize what is meant by the distance between the two points R and I in this 4-dimensional vector space. Well, okay, so this is what I'd like to examine. How far away is the 90-degree rotation from the identity? What is that distance? Well, by definition, it is the maximum of running over all vectors in the unit ball of the norm. Let me stick to using single bars where I said I would use single bars of the norm of this So that means the max over the unit ball of, so this would be, this is a pointwise difference. So this is I of x, which is x, minus r of x, whatever that is. And this is vector norm here. And I guess this is something we can visualize. So if I put R2 here, so this is R2, this is not the vector space in which these are points. So we're not going to find R and I living as points here. So that's not what I'm drawing. But what I'm drawing is the domains of these functions. So here's a picture of the closed unit ball. And what I'm doing when I talk about this real number, the distance between I and R, is I'm saying, look at all the vectors in the unit ball. So let me show you an example. This vector x. This is a x in the unit ball. And look at the distance between Ix, which is x, and Rx, which is x rotated by 90 degrees. Rotated that way by 90 degrees. So it would get rotated like that. Is that how a 90-degree rotation works? No. Get rotated like that. And this distance, that would be the value this takes for that particular x that I started with here. On the other hand, so what I want to do to get this number, the distance between I and R, is I want to look at the maximum of all of those. So where should I put this starting point in order to maximize this number? Definitely I should put it on the boundary to get the difference vector to be the longest. So let me not even consider ones inside. And in fact, in general, you can prove that this is the same as taking the max on the unit circle. So here's a random looking vector on the unit circle. Here's the 90-degree rotation of it. So there's Ix, there's Rx, and then there's the distance. And no matter where this vector starts, if I take the 90-degree rotation of it, it looks like I'm going to get something of the same length. And what is that length? So let me look at these two easy ones here. It's root 2, because this is a unit ball. So all of these lines that I'm drawing have length root 2. So I expect that this is actually max of a bunch of vectors, a bunch of lengths of vectors that all have length root 2. So I guess that this is root 2. So I guess that the identity linear map is distance root 2 away from a 90-degree rotation. Okay, let me do away with the picture and see if we can prove that guess. So what I'm doing right now is not particularly useful. I'm just toying around with the definition just to get some kind of feel for it. Okay, so I want to show this is root 2. Well, it's the max of a bunch of things. So if at least one of those things is root 2, then this is at least root 2, and that would get me one useful inequality. So this is definitely going to be greater than or equal to one of the things that it's the max of those things. So one of the things in the set that this maximizes is I minus R applied to, and then let me just put the vector 1, 0 here. I don't know, maybe I'll write it like this, 1, 0. So this would be the vector norm of 1, 0 minus, I guess 1, 0 gets rotated to 0 minus 1, if I follow the rule of this matrix. Oh, I made a mistake. I'm sorry. This doesn't make any sense over here. This should be this matrix applied to x. The output is supposed to be a vector. Yeah, so over here I get root 2. Okay, so this is at least root 2 because one of the things in the set that it's supposed to be maximizing is root 2. Can I show that it's at most root 2? So let's see. Let x be in R2. Assume I have a random vector, let's call it x comma y, whose norm is less than or equal to 1, so it's in the unit ball. Then the norm of this applied to that vector is the norm of xy minus, and here I should get, let's see, this matrix applied to xy is y minus x. And that gives me the norm of x minus y, x plus y. Alright, so that would be the square root of x minus y squared plus x plus y squared. And if I square this out, I get x squared, y squared, and minus 2xy. Squaring this out, I get x squared, y squared, plus 2xy. So the minus 2xy and the plus 2xy cancel, and I get square root 2x squared plus 2y squared. So I have square root 2 square root x squared plus y squared. So square root 2, well, that's just less than or equal to square root 2, because the square root of x squared plus y squared is assumed to be less than or equal to 1. So that proves that a rotation matrix is exactly square root 2 away from the identity matrix.